It's math time with Heinz. It's math time with Heinz. Math time.
Hi everybody, welcome to lesson 6 here, where we're going to talk about even more domain and range questions. So in the previous lesson, we learned what domain and range are and how we can describe them using that interval notation. And today we're going to practice that a little bit more. So to get us started here, let's determine and state the domain and range of the function shown below. So again, this is a function because it passes the vertical line test. Every x value goes to one y value. So let's talk about the domain and range. So when we talk about domain, remember, we're talking about the inputs to our function. We're talking about the x values. So I'm going to look on my x-axis, how far left can I go, all the way to how far right can I go. That's how we describe the domain of a function. So the domain is how far left can I go, which is 0, comma, how far right can I go, all the way to the number pi. And I don't see any open circles, so I'm going to put closed brackets around them, because that means I can actually plug in a 0. I can actually plug in a pi. I can equal those values. The range, we're going to play the same game, but we're going to go from low to high on the graph. What are my possible output values? When we see range, we have to think of our y values, our outputs. So how low can I go for my range? Well, this is the lowest point, and then I hit every point in between up to that highest point there. So I go from -3 all the way to +3, and I include them, so -3, 3, and I'm going to include them with square brackets there. So when we describe the domain and range, we're describing these are the numbers you can plug in, any number from 0 to pi, and then these are the numbers the function spits out, any number from -3 to 3. So let's talk about our number system, because sometimes we deal with real-world functions instead of just silly graphs like this. So the story of our number system is we started with the whole numbers. We start with the set of whole numbers, which is 0, 1, 2, 3, and so on. 4, 5 are counting numbers plus 0. So our whole numbers is our starting number system. We can add these numbers together and everything's good. The problem is when we want to start subtracting these numbers. We want to start subtracting these numbers at one point, and when I try to do 2 minus 4, we get that number that we call -2, which is not an integer. So what we have to do is expand our number system to the integers. So the integers are the same numbers. It's the whole numbers, 0, 1, 2, 3, and so on, and they're negatives. So we get our numbers and they're negatives. So negative infinity all the way to positive infinity, but it's only those nice integer values. It's the whole numbers and they're negatives. This allows us to subtract the now. I could do 3 minus 7 and get -4. So the integers took addition and allow us to add and subtract now. So the integers is just an extension of our whole numbers. Rational numbers, well, the first 5 letters there is ratio. So we can also multiply. We can add and multiply. We can add and multiply with our integers as well. Add, multiply, and now subtract. Rational numbers, well, I want to add in the operation of division. I want to do 2 over 3. That's not another integer, so we came up with the rational numbers. And if you look here, it's ratio. So the rational numbers are the ratios of two integers. So it's the ratio, a rational number is the ratio of two integers. So it's a over b, where a and b are integers. So it's a fraction made up of integers. The key thing is you can't divide by 0, so b can't be 0. But when you think of rational numbers, I want you to think of positive and negative, right? Negative numbers are included there. -2/3 is a rational number because it's a ratio of two integers. Rational ratio, it's our fractions. When we think of rationals, it's our fractions. So then we get these other irrational numbers. Like if I take the square root of 3, the square root of 2, we get these crazy irrational decimals. These are decimals that never end or repeat. Decimals that never terminate or repeat. There's no pattern in them. So pi is an irrational number. So irrational numbers is any real number that's not rational. So what is the real numbers? The real numbers is the rational numbers. If I take all of those fractions and anyone who's not a fraction, that's what makes up the real number system. So if I was to make a little picture of our real number system here, so this is my real numbers, is that big box. That box gets divided in half, right? The real numbers is that whole big box there. So let me put that on the outside. This is real. Some of them are rational and some of them are irrational. You're one or the other. You're not both. So I got all my fractions in here. Some of my fractions are integers and some of my integers are whole numbers. So whole numbers is nested inside of those other number systems. Every integer is rational. Every whole number is rational. So I get these number systems nested inside of each other like those little Russian dolls. That's how those number systems work. So the real numbers is really both my fractions and my crazy not fractions combined together. And that's what makes up our number system. So you need to know these. It's kind of vocab here. You got to know what these words mean. Whole numbers, integers, rational, and irrational. You got to have to know what those words mean. Because we encounter problems like this when we deal with a function and we want to talk about its domain. So let h of n represent the number of hours it takes to assemble n engines. So let's talk about what this function does. What are my inputs? I'm inputting what is n, the number of engines. How many engines am I assembling? So this is engines. And the output, what does it equal? I'm outputting hours. I'm outputting hours. So I want to know the appropriate domain for this function. So what's the appropriate value of set of numbers for n? Well, are whole numbers okay? Can I make 0, 1, 2, 3, 4, 5 engines? Yeah, that makes sense. I can make 0, 1, 2, 3, 4, 5 engines. What if I go to the integers? What's wrong with that? We can't have I can't do h of -3. How many hours does it take me to make -3 engines? So integers are bad because there's those negative numbers. We don't want negatives. We don't want negatives. We do not want negatives. And any rational number, any fraction, I'm not making a fraction of an engine. So those also go away. We don't want fractions. We don't know fractions allowed. So the best set here that we could use is the set of whole numbers. Because I'm talking about the inputs. I'm talking about the input value of n there. So most of the time, I hate to say it, the answer is whole numbers. There's a couple times where it's not. A construction company uses the function f of p, where p is the number of people. So p is people here. I'm inputting the number of people, that's my input, to model the money. So this equals the money. My output is money. What would be a reasonable domain? So I don't care about that I'm outputting money. I'm dealing with people here. So what would be appropriate? So positive integers. So it's the integers, -3, -2, -1, 0, 1, 2, 3. But I only want the positive ones, so I'm going to get rid of all those guys. Positive real numbers. Well, pi is a real number. Can I have pi people? No, I can't have pi people, or I can't even have 3/4 of a person. That'd be bad. Negative integers? No, I don't want negative people. I can't have -4 people working on a construction project. And again, I can't have negative people. So positive integers is my best guess. So you have to use common sense and kind of a process of elimination when you encounter these multiple choice questions here. An online company lets you download songs for 99 cents each after you've paid a $5 fee. What would be an appropriate domain? So you're inputting 99 cents per song. So you're inputting songs and the function outputs the cost. So again, we're dealing with domain. We're dealing with inputs here. I want to deal with the songs. So rational numbers greater than 0. Well, rational means fraction. So can I download 2/3 or 7/8 of a song? I don't think I want decimals here. Songs are whole numbers. Whole numbers greater than or equal to 1. 1, 2, 3. That looks pretty promising. 4. I don't know why I wrote 4. That looks pretty promising there. Let's see why the other ones are wrong. Integers means negative, less than 0. -2. No, I don't want negative songs. I can't. I'm dealing with my inputs here. Whole numbers less than or equal to 1. No, I want to be 1 or more songs. So let's go with choice 2. So again, there's that common sense factor that you gotta develop when reading these. But you have to know these vocabulary words of what is rational, what is integer, what is real. A store sells self-serve frozen yogurt. We got to go to toppings here. The function C of W represents the cost. So this equals the cost. That's my output. After weighing, so this W here is the weight of my froyo. An appropriate domain. So I'm dealing with domain here. I'm dealing with the weight. I'm not dealing with the cost. That's my output. I'm dealing with the weight. So when I get my froyo and put on my my cookies and cream frozen yogurt with some M&Ms, some cookie dough, some chocolate chips, I like a nice chocolatey frozen yogurt. When I input W, when I weigh it, what are some possible weights? It could be 3 ounces. Could it be 4.1 ounces? Does that make sense? That I have decimal representations for the ounces? Yeah, I could have 4.7, 5.1 ounces of frozen yogurt. Negative, I don't want negative. Negative frozen yogurt is bad. I never want negative frozen yogurt. So integers, that's got negative numbers in it. Rational numbers, that's my fractions, but that also has negative. I want non-negative. So now I need to decide, do I want just the nice whole numbers and their negatives? So this is really whole numbers here. That's really whole numbers. Do I want 1, 2, 3, 4, 5? Are those the only numbers I'm allowed to plug in? Or do I want to expand it to rational numbers where I'm plugging in fractional values? This is a tough one, but I think I want to include the decimals there. I want to include the fractional pieces there because my frozen yogurt automatically doesn't go from 3 ounces to 4 ounces. There's wiggle room in between. All right, let's practice here. So the way that this is going to work is I'm going to pause the video and let you do number 5 on your own, and then you will check your work with mine. So state the domain and range of the following functions. All right, so pause the video and see what you do. See if you can go, remember, domain is your input left to right, range is your output low to high. So this is left, right, range is low, high. So let's see what you got. Okay, so how far left can I go? Well, I need wrong color, Heinz. There we go. How far left can I go? 1, 2, 3. That's -4. And I go all the way over here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So my domain is every number from -4 to 9 with brackets. While my range, how low do I go? That's the lowest, right? That's the lowest y value. That's the first elevator floor I get off on, which is -2. And then I get off on every floor. I'm hitting every y value in between all the way up until 1, 2, 3, 4. So my range is -2 to 4. And make sure you're labeling which one's your domain and which one's your range and not just writing 2 different intervals. All right, I got a nice little U-shaped graph over here, but those arrows mean it goes on forever. So it goes on forever that way. So the domain is -infinity to +infinity. It goes on forever in both directions. While the range, how low do I go? 1, 2, 3, 4, 5, 6, 7. -7's as low as I go. And how far up do I go? Well, it never stops. Those arrows keep going up forever. So -7 with a bracket, because I can touch that point, going up forever to infinity. Just make sure you're always going low to high. That's a common mistake that I see from people. Low to high. Hopefully you did well on those two. State the domain and range of the square root of x minus 2 plus 3. Well, let's look at a graph of this function. So I'm going to go to my calculator. I'm going to go to y equals, and I'm going to look at the second square root of x minus 2. I need to get out of the square root, plus 3. I think that was it. Yes. So let's look at a graph of that function there. There we go. And if I look at my table of values, that'll kind of, I see these errors. So it looks like the graph is starting at 2. The graph is starting here at 2, and then it goes on forever in that way. Let's see if I can drag that over here nicely without causing chaos. No. There we go. Got it. Love it when technology works. So how far left do I go? Well, I think I'm starting here at 2 and going on forever to infinity. So the domain for that is start at 2, go on forever. The range, well, how low do I go? Well, that point is the lowest. I think it goes up from there, right? So the lowest it goes is 3, and it goes up forever. That graph keeps chugging its way up. So the range goes from 3 included up to infinity. Not too bad. Again, when I talk about domain and range, I want to be looking at a graph. So let's do this next one, the absolute value of x plus 3 plus 2. So I need y equals, clear that out, absolute values in math over the number, there it is. Absolute value of x plus 3 plus 2, x plus 3 outside plus 2. So we should get that V-shaped absolute value graph there. There we go. And let's see how I do. Let's see if I can drag it over again. Zoop. Excellent. Here we go. All right, left to right. Absolute, looks like that goes on forever there. Those absolute value arrows never end. So my domain of my absolute value graph is negative infinity to infinity. It's all real numbers. I can plug in whatever number I want to this function and it goes on. I'll always get an output. The outputs, though, how low do I go? What's the first elevator floor? If I go horizontally, what's the first floor I get off of? Right there. Right there at y equals 2. And then it goes up forever and never stops. So the range appears to be 2, comma, infinity. Remember, infinities always get parentheses. If you can actually touch the point, that's when it gets a square bracket. On the set of axes below, graph me this function over this domain. So I'm giving you the domain. Those are your inputs. You're only allowed to plug in -1 all the way up until 4. 0, 1, 2, 3, 4. Those are the only numbers I'm allowed to plug in. So let's make our table of values on our calculator here. So what do we have? X squared, clear it, x squared minus 2x plus 2. Minus 2x plus, I forgot the x. Get it together, Heinz. Plus 2. So I'm going to look at my graph here. So it's that nice U-shaped curve, but I just care about from -1 all the way until, I believe it was 4. So let me drag that over here so I don't have to keep flipping back and forth. There we go. So my x values, I'll move it, are from -1 all the way to 4. So 5, 2, 1, 2, 5, 10. So that's all I'm graphing. I know that curve goes on forever, but I said in this problem, graph it over this domain, start, stop. So I'm not going to graph that whole U shape. I'm only going to graph those points. 1, 2, 3, 4, 5. 0, 2. 1, 1. 2, 2. 3, 5. And then 4 all the way up till 10. So again, no arrows on this graph. Normally this curve gets, that's terrible. That is terrible. We'll do that again. Normally this curve gets arrows, but I'm going to stop right there because I told you where to start and stop. And finally, I ask you for the range. What is the range of this graph? Well, range is low to high. How low do I go? 1. Oh, do I go on forever? Normally I do, but I told you to stop. So the range is 1 to 10. All right, hopefully this was some good practice with domain and range, and you need to study up on what these number systems are. You can't answer these questions unless you know what I talk about when I say whole numbers, integers, rational, and irrational. You got to know what those are. We start with our nice counting numbers, then we throw in their negatives to make them integers, then we throw in fractions to make them rational, and then the irrationals are the crazies. This is never the answer. I hate to say it, irrational numbers, never the answer. And on that note, I'll see you guys in the next lesson.